Okay, it's now week 2 on Monday. I hope homework 1 is working okay for you guys. It's doing a few hours. I've decided to make my Monday office hours, you can come in person too, okay? At the beginning I said everything's gonna be online via Zoom. So Monday will still be Zoom, but you can also come to my office. So I'm on the 8th floor of the Math Sciences building. You take the elevator up to the 8th floor. 8105 is directly across the elevator. So the Math Sciences building's right over there, right? And then you've got the walkway with all the vending machines. So there's an elevator right at that entrance with the vending machines. Take that elevator up to the 8th floor. Directly across from the 8th floor is 8105. I'll have the door propped open during my office hours, and you can walk in, and it's kind of a suite of offices, and mine's in the corner, 8105J. But during office hours, I'll just be kind of hanging out in this little lounge area inside 8105. So that will be that. If you can't come live or something, also I'll have you can also come via Zoom. I think some of you are in a class though at that time, and I didn't realize it started at 12:30, so I apologize for that. So all of the other office hours you can come via Zoom, but if you wanted to meet in person, that's available. Okay, let's take a look at our topic for today, which is where we are introducing Monte Carlo integration, this topic, this idea of getting an estimate via random sampling, all right? And so on Friday, we were working with the Spaceball example, right? And we said, we had this prior distribution for what we believe the player's batting average to be. Batting average being some proportion, what proportion of at-bats results in a hit. And we said prior to saying anything about the player's data, the prior distribution could be modeled with a beta distribution. And that beta distribution would have shape parameters 81 and 219. Admittedly, those numbers were selected arbitrarily, but they reflect a bit of our knowledge or opinion regarding what a player's batting average might be. Now, after we observed the player at 10 at-bats, this player had 5 hits, and so we made an adjustment and we said after or posterior to the data, our beliefs about the player's batting average is now described with a beta distribution with these parameters, 86 and 224. And we asked the question, if this distribution, this beta distribution, describes the player's batting average, what is the probability that the player gets 2 hits out of 3 at-bats at the next, kind of in the next 3 at-bats? And, we saw it answered analytically, we saw it answered using just one estimate or one value, but we also saw the answer that we got via Monte Carlo. And what we did was we said, I am able to generate values from the beta distribution. I'm able to generate random values from the beta distribution, and we got 1 million of these values. And we take that sample and we basically just plug it into the function that we're interested in. We're interested in the function, which is 3 choose 2 theta squared 1 minus theta to the first power. So we just take all of those values that exist in our sample, 1 million of them, we plug them into function g, and we take the mean of that result. So basically we say, here's one random value of theta, let's plug it into g. There's another random value of theta, let's plug it into g. We did this 1 million times, and we took the average of all 1 million, and we get a number 1.1671577, which we showed was very, very close to the true analytic value if you were to do the actual integral from 0 to 1 of all possible values of theta. So this is where we left off on Friday. And this thing that we did here is kind of your first Monte Carlo estimation, first Monte Carlo integration, because ultimately we are computing the value of this integral. And so today we're going to kind of develop this a little bit further. This concept is still very simple. Generate random values of your random variable x, plug those into a function, take the mean, and that's going to serve as your Monte Carlo integral estimate, okay? And the idea here is just in general, let's say you have a random variable x. If we apply some function h of x, h to the random variable x, what is the expected value of h applied to the random variable x if x is defined by the PDF f? So this notation, it's a little bit strange. There's kind of a lot of letters going on here. And again, what does this mean? It is the expected value of the function h applied to the random variable x, and the random variable x is defined by the PDF function, or the PDF f. Okay? So that's how these different elements come into play, right? So you could have a different random variable, maybe a random variable y, which has a different PDF, maybe a PDF letter G or something, and you'd have e, the expected value sub g of some function h or some other function, q, whatever it is, applied to some other random variable y or something. So again, this is random variable x is defined by the PDF f. If you apply some function h to x and you take the expected value, what would we get? Now, normally you're accustomed to just saying the expected value formula, where h is just the identity, right? You just see e of x, expected value of x. That's found by just doing x times f of x dx, okay? But here we can take any arbitrary function h, and we will take the integral of h of x times f of x dx, okay? And we would integrate across the domain or the support of x, okay? So this thing, this expected value is equal to the integral across all values of x in, I should say, in the support of x, h of x times f of x dx, okay? The integral of the product h of x times f of x. And Monte Carlo integration says you can approximate this integral by just calculating h of x if you take n being a large number, n random values drawn from the PDF f, random values drawn from f, those would be random instances of x, apply h of that to that thing, and then take the mean, which would be sum them up, divide by n. Basically, we're just saying this integral is approximated by this, and we're just putting this in mathematical notation. Okay, little side note on the notation. You've got random variable x, which says x is an element of curly x, where curly x, the region curly x, is the support of x. That is to say, this is where the PDF is greater than 0. Outside of the support of x, the PDF is equal to 0. So if we're talking about the beta distribution, the support goes from 0 to 1, as the beta distribution defines proportions, and proportions are always between 0 and 1. And you can't have a proportion greater than 1, can't have a proportion less than 0, okay? If we're talking about the normal distribution, which goes from minus infinity to plus infinity, the support is basically the real number line. If we're talking about, say, the chi-squared distribution, the support would be all positive values, okay? If we're talking about the support of a binomial, then it would be positive integers from 0 to n, whatever n being the number of things you have, okay? And the p, if it's a binomial, then it's technically a PMF, okay? And again, the idea being, if you were to integrate integrate f of x across the support, that integral is 1, right? That's a defining attribute of a PDF. If it doesn't integrate to 1, it cannot be a PDF. The integral across all possible values has to be 1. And so if we were to just do the expected value of x, this is just the expected value of x of some random variable with density function f. Okay. All right, so again, how does this work? The process works exactly the way we've seen. I don't think this is a huge jump. We have to be able to generate values of x from said PDF. Okay? Now we have a lot of functions in R that generate random values, right? So if f is a normal distribution, we use R norm. If it's a beta distribution, R beta. If it's a gamma, R gamma. If it's exponential, R exp. Whatever, there's a ton of things. There's even more if you load up some library. So pretty much any PDF that you can think of that has a name, there's probably a function in R that is able to generate it, right? From the T distribution, chi-squared distribution. How many distributions can you name? Poisson, whatever. Okay, so anyway, you just generate a bunch of these things. With R, again, it's very easy. You just use R whatever. And then you have a function, h, apply the function to all of those things. Again, this n is probably something on the order of 10,000, 100,000, a million, maybe even more, depending on how computationally expensive it is to generate these things. You guys, we live in this time of luxury where we can generate random values from the computer very, very, very easily. And this idea of generating values, random uniform values, that was, now it's like 30 years ago, but like up until the 1990s, this was like, it was hard generating random uniform values. And now it's considered kind of a solved problem, okay? And so if you were to take, I don't know if they would have a Monte Carlo methods class in the 90s, but if you were to take some equivalent of that, a large portion of your class would be spent on just talking about how do we generate random uniform values. And maybe we'll have a brief chat about that later. The answer today is it's complicated, but it works, okay? And now we just say, all right, it works. Okay, much like, do you know how to take the square root by hand? Okay, that used to be something you had to learn in like high school. If you were if you were on the calculus track, okay, you'd have to learn like how to take the square root of a number by hand because you didn't have calculators. But now it's like, oh, the calculator is able to take the square root, and that's good enough for us, okay? So nobody knows how to take the square root by hand anymore. There is a way to do it. I don't know how it works. You can probably find it on YouTube, and some person will be like, hey, everybody, and you can do it. But we don't need to learn, right? We don't need to learn how to generate random uniform values because it's kind of solved for us. We don't need to learn how to take the square root by hand. It's solved for us. We know how it works, anyway, okay. So anyway, you just apply the function h to all of those random values that you've generated, and you're going to get an estimate of whatever this expected value is, expected value of the function applied to some random variable x, just by taking the mean, the sample mean. That's it. You generate 1 million of these things, you take the sample mean of that thing. And that's it. That's classic Monte Carlo integration. But maybe we should talk a little bit about how it works, why it works, and maybe some properties of this. Let me go ahead and give you your first view quiz answer for today. Today's view quiz answer, first one, A. A as in apple. A as in apple. Okay, this is not a formal proof, but hopefully it will provide a bit of intuition about why it works, okay? I always struggled with formal proofs, just because, you have to make everything watertight. You have to think about all of these edge cases and stuff, and that was always something I struggled with a little bit. So this is not a formal proof, but it should provide a bit of intuition here. So the idea here is that Monte Carlo integration works basically because of the law of large numbers. The idea being that as n, the number of random samples you draw, as that approaches infinity, then your random sample is going to become more and more representative of the actual distribution, right? So if you generate a the distribution generated by F, your random sample, as you take more and more and more, will basically become more and more representative of that thing. Okay? Maybe slightly more formally, we can say the empirical cumulative distribution function, okay, that is to say capital F, right? Capital F represents the CDF of a function, and here we're saying capital F hat, the CDF of a function, based on the sample, converges almost surely to the actual CDF, right? And have you talked about modes of convergence? It's a bit of like a grad level topic, and man, this was like the course in grad school that gave me so much grief, okay? But if you were to pursue like a PhD in statistics, or if you were to pursue like a master's degree in statistics and decide to take a theoretic course, you'll probably have something where you have to talk about modes of convergence and probability. And there's all, you know, there's converges surely, converges almost surely. You can read this. Look up modes of convergence on Wikipedia, and you can, convergence of random variables. This is what we want. Okay, so look up convergence of random variables, convergence in distribution, convergence in probability, almost sure convergence, and they have different examples here that could be fun reading if that's what you're into. I will not shame you. So anyway, what this says is as you go into get more and more values from your random sample, it becomes like the actual cumulative distribution function. I think we have an intuitive sense of that. And so what we're saying is that this estimate, where we're basically taking the mean of some of the function h, right? This is h bar sub n is what we've designated as our Monte Carlo estimate. We're saying that thing converges to this theoretic thing as n approaches infinity. Okay, so what does it mean for the empirical CDF to converge to the actual CDF? Basically, I just have a bunch of pictures to show you what's happening. And again, a bunch of pictures does not make a proof, but hopefully it provides a little bit of intuition, right? Okay, so what is the empirical CDF? Well, first of all, let's talk about the actual CDF, right? The CDF, the empirical CDF is if you've got some set of random variables drawn from the cumulative distribution function, then your empirical CDF is going to be the number of elements in the sample less than some value t divided by n, right? So if you're talking about, well, let me just show you some examples here, okay? Versus the actual CDF, okay? What's the definition of the actual CDF? The actual CDF for some random variable x, it's the, it's the function of t, whereas t goes from, negative infinity to positive infinity or whatever it is. And so at negative infinity, the CDF is always 0, and at positive infinity, the CDF is always 1, okay? And then what happens in between is basically what defines your CDF. So if you're thinking about the normal distribution, for standard normal distribution, if I plug in t equals 0, what's the probability that x is less than t? 0.5, right? So the CDF at 0 is 0.5. This is basically the Q norm on R, right? You type in Q norm 0, you get 0.5. So what would I get if I type in negative 1.96? 0.025, right? These are the numbers you got to know as a stats major, right? So if I type in 1.645, 1.645 would be 0.95, right? So, okay, and then 1.96 would be give me 0.975. 2.33 would give me 0.995? Oh, I don't know. Okay, maybe I don't remember that one. But anyway, but that's what we have. And basically, we're getting an estimate of this. We're estimating the actual CDF, by taking, looking at my random sample. So if I say, let's say I generated 100 values from the normal distribution, and I say, okay, out of my 100 values from my standard normal distribution, how many are less than 0? Okay, let's say 48 out of 100 are less than 0. My estimate of the empirical CDF, or my empirical CDF would say 48 are less than 0, 48 are less than t, in our case 0. 48 divided by 100 is 0.48. So my empirical CDF estimates the CDF to be, 0.48, where in reality it's 0.5, okay? But if I get a larger and larger sample, like if I generated a million values from the standard normal, and I said what proportion is less than 0, I'd probably get something very, very, very close to 0.5, okay? And that's basically what we're doing. So this empirical CDF is an estimate of the CDF, and we can see as we get more values, this gets closer to the actual thing. So this is what we have, right? Okay, so your distribution functions in R, I think you guys know this, right? D is for the density. Can densities be greater than 1? Densities can be greater than 1, okay? Densities can be greater than 1, okay? P is cumulative probability. Can cumulative probability be greater than 1? No. Cumulative probability is always going to be between 0 and 1, okay? Q is for the quantile, and what can the quantiles be? Can I get a quantile greater than, like if I plug in a number here, can Q norm spit out something greater than 1? Yes, okay? So basically for P norm, the inputs here can be anywhere from negative infinity to positive infinity, and the output will be between 0 and 1. Whereas Q norm, the inputs are only allowed to be between 0 and 1, and the output can be anything from negative infinity to positive infinity, right? So if what would happen if I type in Q norm 1? This is the CDF, the inverse CDF. Okay, I don't have time for that. Okay, R is for random. I'm like, I want to show you this, but then I'm like, oh, I got to balance time. But I just want to show you. But RStudio is refusing to load. Okay, here we go. All right, let's make this, oh no, bigger. Oh, geez, okay. All right, so let's do Q norm. Q norm 0 will give me Q norm 0 will give me negative infinity. Q norm 1 will give me positive infinity, okay? Whereas P norm 0 gives me 0.5. P norm 1, does anyone? Okay, P norm 1 gives me 0.8413, right? So this is, if you go to z-score equals 1, what's the area to the left? 1 standard deviation above is around 84%, something around there, right? So that's how we say, P norm 1. What's P norm 1 minus P norm negative 1? You guys remember your empirical rule? Man, you guys are breaking my heart, right? 68, 95, 99.7, right? P norm 1, P norm 2 to negative 2, what do we get? I just gave you the answer, right? It's 95, and then P norm 3 to minus 3 should give us around 99.7, okay? All right, that's P norm. Whereas Q norm, if I plug in, right? What if I want 0.95? What is this going to give me? 1.645, 0.975, 1.96, right? Q norm 99, 0.233, Q norm 995, 2.58. Okay, well anyway, that's what we have. All right, so this is an example. Here I'm doing random uniform. I'm saying give me 5 random uniform values. Okay, so that's going to be 5 values between 0 and 1, random uniform. I'm sorting them. And the first number that I got, 0.2, the next value I got was 0.2665. The next value is 0.373. And so this is what my empirical CDF is, okay? We're asking if my number is 0.5, okay, if I go to 0.5 here, what proportion of my sample is less than 0.5, okay? So theoretically, the amount less than 0.5 is 0.5, but in my sample of 5 values, what proportion is less than 5? I've got 3 values less than 0.5, and so the empirical CDF at x equal to 0.5 is 0.6, okay? The empirical CDF for any value between 0.372 and 0.572 is 0.6, because 3 out of the 5 values are less than that. Are we okay with how this empirical CDF is calculated? Okay. All right. If I take, this would be what the theoretic CDF looks like. Okay. If I took a larger sample, 10 values, okay, 10 random values, we're just asking what proportion of values are less than, 0.5 or 0.8 or something, and we could see we get something that, deviates a little bit from the red line. And as I take more samples, so here's a random sample of 100, okay? And again, it's a stair-step thing, again, because it's always what proportion is less than this number. And so if it's a number in your sample, it jumps up, and then it stays flat until it becomes the next number in your sample. So what proportion is less than this? This is what we get. And as n becomes larger, here's n is 1,000, okay, we can see the empirical CDF starts to align quite closely to the theoretic CDF. Here it is at 10,000, n equal to 10,000, we get pretty close alignment, okay? And this is just the idea that as n approaches infinity, the empirical CDF approaches the true CDF, okay? Similar thing, here's the normal distribution. And we can just say, give me 10 random values from the normal distribution. What proportion of values? Okay? And so again, with only a sample size of 10, this doesn't look that great. Here it is with 100, okay? And we get something a little bit closer alignment. With 1,000, the empirical CDF gets closer to the theoretic CDF. And at 10,000, it's pretty close. All right, and all to say is that the empirical CDF, indicated by big F hat, gets closer to the theoretic CDF, big F, right? As n gets larger, we can see the empirical CDF, based on the sample, gets closer and closer to the actual CDF. All right, this is not a proof, but hopefully it just provides a bit of intuition as far as why this is working, why this Monte Carlo integration kind of works as you take a big sample. Okay, let me go ahead and give you your second view quiz answer. Today's second view quiz answer is E. E as in elephant. E as in elephant is your second view quiz answer. All right, so let's talk about these properties of the Monte Carlo estimator. So the Monte Carlo estimator, again, is just apply the function to your random sample, take the mean of those values. That's your estimate of the expected value. Okay? This is what we want. We want the expected value of h applied to the random variable x. And our Monte Carlo estimate, okay, which again, defined way back here as just the sample mean of h applied to a random sample, that itself is an unbiased estimator. It's an unbiased estimator. That is to say, the expected value of the estimate, the expected value of h bar n, this is the Monte Carlo estimate, the expected value of this thing is equal to the expected value of the actual thing we want, right? So this thing is equal to the thing we want. The expected value of this thing is equal to the thing we want, okay? And of course, any one thing that you get, right, just like the sample mean is an unbiased estimator of the population mean, you know, any one instance is not going to be a perfect thing, but in the long run, your sample mean will be unbiased, will be centered around the population mean. Same thing, okay? And we can look at this by saying, okay, well, here's my Monte Carlo estimator as defined here. What is the expected value of this? Okay, well, this is just a constant, 1 over n, okay, multiplied by, you know, this is what's subject to the randomness. So the expected value just only becomes the subject to this randomness. All right, so what is the expected value of some function applied to draws from the random variable? Okay, well, if you're truly generating values from the random variable, then it becomes the expected value of that becomes the expected value of the expected value of the random variable. Okay, what about the variance of this Monte Carlo estimate? Okay, so the idea here being, if one person says, I'm going to estimate, you do Monte Carlo integration, here's a sample of 1,000 things, right? And we have everybody across the room estimate the, you know, what proportion of hits will, what's the probability the player gets 2 hits out of 3 at-bats, right? And I have you each generate 1,000 values from the beta distribution. I each have you apply that function to those 1,000 values, and then you each get an estimate. All of your estimates are going to be slightly different from each other, but they're also going to be very close to each other. What is the variance between everybody's estimates? That's what we're asking. What is the variance of everybody's Monte Carlo estimate? Okay, so, well, here is the definition of the estimator, all right? We're asking, what is the variance of this estimator? Okay, so we're asking, what's the variance of this? Basically, it's a sample mean, okay? And so we can say, all right, well, it's the sum of 1 over n of h of basically your first draw, h applied to the second draw, all the way up to the nth draw. We got 1,000 random draws, all right? And we can pull out 1 over n, right, from a variance, and it becomes 1 over n squared. And so the variance of all of these things, because all of these draws are IID, I can combine all of their variances, okay? So all of these draws, all n of these, all are IID, they all have the same variance, okay? So they're all gonna have the same variance. So I've got the variance of this is 1 over n squared times, how many of these do I have? I've got n of them, n times the variance of h of x. And so your overall variance, the variance of your estimate is 1 over n times the variance of, you know, whatever this function is. Okay, so you think about what's the variance of the random variable, in this case the beta distribution. So you say, what's the variance of your beta distribution with, you know, shape parameters 86, 224, or whatever it is that you're looking at, okay? And then how big is your sample? Okay, if everybody's estimating, you know, the proportion of hits, or the probability that the player gets 2 hits out of 3 at-bats based on 1,000 random draws, the variance is going to be 1/1000th of, you know, the variance of this random variable, okay? All right. The titles just get worse. Monte Carlo estimate of the variance of the estimate. We could kind of do this thing where, well, I don't want to have to go through this mathematical calculation myself. We can get a Monte Carlo estimate of this thing, right? So if we don't know, right? If we don't know h of x, right? So here I said it's 1 over n variance of h of x. What if I don't know this thing directly? What am I supposed to do? Okay, we can also estimate it, right, using some identities and the Monte Carlo methods, right? So we said the definition of the variance for some continuous variable y, the definition of the variance is y minus the expected value of y. You take the square difference, multiply it by f of y dy, okay? And then, you know, you can simplify this to, you know, expected value of y squared minus expected value of y quantity squared, things like that. But here, if y, right, so x itself is a random variable, and then h, if you apply a function to x, that quantity itself is a random variable too, because it's subject to randomness. So we're going to say, let's say we have some random variable y equal to h of x. What is the variance of y, right? Because back here we say, well, what's the variance of h of x? Well, I'm not sure, right? It's kind of like if I have x as a random normal variable and I'm going to square it, what's the result? What's the variance of x squared, okay? Maybe you can go through the math and figure that out. Maybe you don't want to, okay? Can we just do a Monte Carlo estimate of this thing? Sure we can, okay? So we're going to say the variance of this thing is 1 over n times the variance of h of x. And we're going to say, well, I don't know if I don't want to figure out variance of h of x directly, okay? So we're going to define this function, okay? The variance function is h of x minus e, the expected value of h of x, okay? And what we're going to do is we're just going to say, all right, let's let this thing be some new function, g, right? So now now it's in the form of the Monte Carlo method directly, right? So we've got g of x times f of x, okay? And so we can approximate this integral by using Monte Carlo methods again, okay? So we're going to say, all right, let's estimate this thing just using the Monte Carlo way, except we've defined g now, this function g, as basically the definition of the variance. Okay, so if I plug that in, this thing, okay, this whole integral is approximately going to be 1 over n times the sum of g of x, okay? And so the variance is going to be 1 over n times 1 over n times basically whatever this thing computes out to be. All right, so this is what we have. And then what we say is, okay, well, what is this part over here? This part is the Monte Carlo estimate, h bar sub n, or h sub n bar, okay? And so this will be the Monte Carlo estimate of the variance of the estimate. And that's this. The variance of our Monte Carlo estimate is estimated by this quantity v sub n, which is 1 over n squared, times, again, you just plug in x to h, and then you subtract off whatever mean estimate you had earlier. Okay, and again, if you think about this h bar sub n is just a sample mean. And so we can apply the central limit theorem, right? Central limit theorem pops up anytime we've got a sum or a mean. And so the central limit theorem says, hey, if you got a sample mean, then that estimate should follow a normal distribution. And what would the mean be? The mean would be the population mean. The variance is 1 over n times the population variance. And so here, what is the population mean? Okay, well, the population mean, we said it was an unbiased estimate. So the population mean is the thing that we're after. And then the variance, okay, we said, well, this is the variance here. And we said, okay, well, you know what, this thing we can estimate using this quantity, v sub n, right? We said the variance of this thing is that, okay? So we're going to plug that in here. And the normal, this will have a normal distribution centered at the population expected value, the true expected value, with some variance quantity, all right? And so we can kind of create some confidence bounds using, plus or minus 1.96, stuff like that. Did I give you your second view quiz answer already? I did. Okay, good. All right, so there's a lot of math on those slides. Let's not get super lost in them, okay? The important things, these are the important things, just to kind of recap all of this stuff, right? Because there's a bunch of math, and the math can be fun, but it could also be, we can get lost, getting stuck in those things, right? The idea, the big idea, We're just drawing random samples of x. Okay, just generating random samples of x. And we have a way, okay, if we can do this, we can estimate the expected value of h, some function, arbitrary function applied to x, right? So whatever function it is, right? So we want to say, take random normal variables and then let's plug it into, say, the sine function, okay? What's the resulting distribution if you took random normal variables and you plugged it into a sine function? Okay, I don't know, right? Well, as long as you can generate random normal values, we can estimate that quantity. What would be the mean, okay? Well, the mean is going to be the expected value. It can be estimated using the Monte Carlo estimate. Just plug in your random normal values that you generated, plug it into the sine function, take the mean of that, and that's going to become your estimate. Okay, and so h bar is just the sample mean applied, a sample mean of h applied to those random draws of x. Okay, and that thing works, right? And then h bar itself is normally distributed. It's if a bunch of people did this thing, followed the same process, everybody's estimate would be centered around the true value, and the variance would, be affected basically by a factor of how big your sample is. Okay? So we can take this concept of Monte Carlo integration and use it to actually perform or estimate integration, right? So let's say you want to estimate the integral of just any arbitrary function. This is some arbitrary function, not necessarily a PDF, okay? And you just want to estimate this on some interval, a to b. Okay? We can basically take what we've learned and apply it here, okay? So this integral may be difficult to calculate, okay? So one thing is we can start off, we can say the average value of this is if we were to integrate the function from a to b on this, we would get the area, and then we just take it, divide that area by the width, b minus a, okay? That's going to give you the average value of h on that interval. And so if I rewrite this, okay, if I just rearrange terms, right, if I say, okay, this thing, and bring in the 1 over b minus a inside, okay, now this is in the form of function times a PDF, right? And I'm integrating this from a to b, okay? And basically, if you say the PDF is the uniform distribution, okay, the uniform distribution from a to b, okay, then the integral going from a to b is the support of that uniform distribution, and 1 over b minus a is the PDF of that uniform distribution. Okay, so if you just think about the uniform distribution, this is the PDF and this is the support. And so now we have the exact formula of basically arbitrary function times the PDF f integrated over the support of x. Okay, and so this is the Monte Carlo estimate for this thing is this thing, and if we want the original value of the integral, we multiply it by the width of the interval b minus a. All right, so here's just kind of a step-by-step thing, but I think we can figure this out. You generate values from the uniform distribution from a to b. You're going to apply that function h to all the values that you generated. You're going to estimate this thing by 1 over n times, by basically the sample mean of h applied to all of those things. And then if you want the estimate of the integral itself, just multiply that sample mean times that width, b minus a, to get back kind of the original area. Okay, so here's just a silly example. Here's a function, cosine 50x plus sine 20x added together, quantity squared. What is the integral of this thing from 0 to 1? Okay, do you want to do this? Okay, it's not fun to do by hand, okay? We can basically anytime I see something like this, I go, all right, let's go to Wolfram Alpha and please give me an answer, right? So what does Wolfram Alpha say? All right, it says if you take the integral of this thing, the integral is equal to 8,240 minus 150 sine of 40 plus 42 sine of 100. I don't know where they're getting these numbers, but that's what Wolfram Alpha says, and we're going to have to trust them, take their word for it, okay? I'm not going to bother doing this. And this is kind of what the function looks like. Geez, what a mess, okay? And it says, okay, well, this thing is equal to 0.96520. Okay, I believe you. All right, this is what the function looks like. What if I wanted to integrate this or get an estimate of this? Okay, so again, Wolfram Alpha says this is equal to this, 0.96520. Okay, what can I do? All right, what do? I'm going to generate 10 to the 5, 100,000 values from the random uniform distribution. Okay, I'm going to generate these 100,000 values between 0 and 1. H of x is defined by this, cosine 50x plus sine 20x squared. I'm going to just apply h of x to all of my random values of x, okay? And maybe I should have named this better, but I call this h underscore x, right? And then what do? I calculate the mean of h underscore x. And my estimate is 0.966863, okay? And, well, the width of that interval is 1, so the estimate of the integral is also going to be 0.966863, okay? It's not a perfect thing. We got the true value according to Wolfram Alpha is 0.9652, and I'm getting 0.96683, but it's pretty close, I would say. It's off by a little bit. Okay, so just to kind of show you what this looks like just for the first, say, 10,000 values, okay? What we're going to do is we're going to take a look at the cumulative mean, just to say, all right, so again, this is the mean after 100,000 values. I'm taking h underscore x is a vector length 100, and so we're getting the mean here. But here I'm going to just say, hey, calculate the cumulative mean, which is basically the cumulative sum divided by the quantity, so this is going to be how many values you've observed. And then we can also estimate the variance. I think I input this correctly. So for any given number m, what is the variance of our estimate? Okay, and then so we're going to apply this. I'm using the apply function. We'll calculate kind of the standard error, take the square root. So what is the result? I'm going to basically add error bars, plus or minus 1.96 times my standard error here. And so the result here, all to say, so in the beginning, the true value again, the true value is something around 0.96520. So in the beginning, there's a lot of, I don't know if you can see this. Okay, it bounces around quite a bit. And the amount of variance that we have is big because our estimate's based on only a few observations. Okay, but as we get more and more and more observations, our variance shrinks, and we can also see that the estimate starts to steady and get a little bit stable. Now, this is a bit of a weird function, right? So if we look at the function, there are parts of the function that are quite tall, other parts of the function that are quite low. So if you think about, what's the estimate? If you take the mean, every now and then you get this huge value, so it jumps up quite a bit, okay? And so that's why you still see a little bit of wiggle here, but we can see it starts to steady out, and eventually as we approach infinity, this thing should approach the true value of around 0.965. Okay, so the big takeaway, again, the important thing, really kind of summed up on this slide, I believe, okay? All right, that's it for today. Let me give you your last view quiz answer. Final view quiz answer is B, B as in bear. B as in bear. Okay, and then again, office hours, I still got them online, but if you want to come in person on Mondays, you can do that as well. All right, have a good day, you guys. We'll see you guys on Wednesday.